In this video, we're going to talk about work and then also kinetic energy. Remember, work is the integral of whatever our force function is. In this situation, we have a variable force. So force is a function of x, x being position. So f of x moves that object of some mass, which we'll refer to m, along the x-axis from x sub 1 to x sub 2, an initial and then a terminal point. And we know the velocity is the derivative of position x. So the derivative of position represents velocity. dx dt equals v. That should just make sense from a calculus 1 standpoint. Now, Newton's second law of motion, force equals mass times acceleration. And this is the derivative of velocity with respect to time is acceleration. So force equals mass times acceleration. If we think about breaking this up using the chain rule, the derivative of velocity with respect to time, acceleration, is equal to the derivative of velocity with respect to x, position, and the derivative of position with respect to time. And so you see that this is balanced the way I've written it, because when the dx's cancel, we still have just dv over dt. So what we know, though, is that dx dt equals v. So we can represent dv dt as v times dv over dx. So I'm going to encourage you to pause for just a second and make sure that what I've talked about makes sense, reading through it and thinking about what I've just talked about. So we want to show that the net work done by the force moving the object from its initial to its terminal position, x sub 1 to x sub 2, work is the integral of the force, integrating that force. And we want to show that that is equal to 1/2 mass times the velocity at the second position squared minus 1/2 times mass times the velocity at the initial position squared. All right, so in physics, we have a note here. 1/2 mass times velocity squared is kinetic energy. So essentially, the net work is the integral of those forces, and that is the kinetic energy at the terminal point minus the kinetic energy at the initial point. All right? Kinetic energy is the energy of a moving object. So the work done by the force equals the change in the object's kinetic energy. And the total work, the net work, can be found by calculating the change in these kinetic energies. So on the next slide, I'm going to derive this for you. So let's think again about how we define force. Force equals mass times acceleration, which is the derivative of velocity over time. So force equals mass times acceleration. And what we showed on the previous page is that we can represent dv dt as v times dv dx. So we want to be thinking about this force as a function of x, not time. So if we wanted to calculate the work would be the integral across that interval from our initial point x sub 1 to our terminal point x sub 2 of that force. And the force that we said above was m times v dv dx. And we need to integrate that with respect to x. So this is my force. This is F. Work is the integral of the force. Now, we want to pay attention here. We're integrating with respect to x. So mass, that's going to be a constant. I can factor that out in front. And I've got the integral from x sub 1 to x sub 2 of v dv dx dx. looking at simplifying this, I have mass, the integral from x sub 1 to x sub 2. The dx's will cancel, and we have v dv. So when I integrate v, and I don't know what v is, but it's going to become a function of x. And when we used the power rule to integrate that, it became squared and then over 2. So all of this needs to be evaluated from x sub 2 to x sub 1. So plugging x sub 2 and x sub 1 into my function, I'm going to have m over 2, and I have v of x sub 2, whatever that is, squared, plus v of x sub 1 squared. Technically, I should maybe put some square braces in here. So looking at what we have, this is the function with an input. This says v of x sub 2. So we're going to be getting an output value from this. And the way I'm going to refer to that output value is v sub 2. It is the velocity at that second or terminal position squared plus the velocity at the initial position squared. So those represent the outputs I would get. And of course, if I distribute my m over 2 to both of those, I have 1/2 m v sub 2 squared plus 1/2 m v sub 1 squared. And at this point, I have proven that this represents the net work. So let's do one short example. So what we just said on the previous slide is that work is kinetic energy, right? It's the same as the kinetic energy, or the change in the kinetic energy, delta meaning change in. So work is the change in the kinetic energies, and the kinetic energy is that change is found by doing the difference of 1/2 mass times the velocity squared. Right? So, in other words, the change in kinetic energy of a body is equal to the amount of work done on that body. So here we have our question. How many foot-pounds of work does it take to throw a baseball 90 miles per hour, considering that the baseball weighs 5 ounces or 0.3125 pounds? Well, we just defined that work is 1/2 mass times the velocity squared. Now, we want to notice that we are in the imperial system, miles, ounces, pounds, all right? So we're dealing with miles per hour, and we want foot-pounds. So I'm going to go ahead and change that miles per hour into feet per second. So velocity is 90 miles per hour. Converting that, that's 1 hour gives me 60 minutes, and 1 minute gives me 60 seconds, and 5,280 feet represents 1 mile. So after this cancellation, I end up with 132 feet per second. I ran out of space there. But so my velocity, instead of using 90 miles per hour, we're going to use 132 feet per second. And we know the weight of this object, this baseball, but we need its mass. And so the mass is going to equal the weight in pounds divided by the acceleration due to gravity. So that's going to give me 0.3125 pounds divided by 32 feet per second squared. And that will give us 0.3125 over 32. And this unit of measure is called a slug. And a slug is a unit of mass. It is accelerated by 1 foot per second squared when a force of 1 pound-foot is exerted on it, right? So a slug has a mass of approximately 32.1 pounds based on standard gravity. It's not going to be a huge concept in this class, but you may hear that term in your physics class. And I encourage you, if you have more questions about those units of measure, to talk to your physics instructor. Now, moving on with our problem. Now that I know my velocity and my mass, my work is going to be 1/2 that mass, 0.3125 over 32, times my velocity, 132 squared, which gives me 85.1 foot-pounds. And that represents the quantity of work it takes to throw that baseball. So, again, email me if you have any questions.